Okay, good morning, students.
Good morning, sir.
Yeah, thank you for responding. And today we will start off with your DEC lab, okay, Digital Electronic Circuits lab. And I hope you have been following your classes, right? Digital electronics classes. And with that, that's going to be the base of your learning. And in this lab, we are going to have all the practical point of view. Okay. So are you all able to see my screen?
Yes, sir.
Okay, thank you. So this is going to be your subject code, okay, your lab code 19 ECL 37, and it's for about 50 marks, and your essay is also for 50 marks. Fine. So the first uh, experiment is going to be simplification of Boolean expressions using K-map and realization of simplified expression using basic and universal gates. So before we get started, can you all tell me what is meant by K-map? You have studied this exclusively in your um, theory, right? So what is a K-map?
It is a tool used to reduce an expression to its simplest form.
Okay, good, Darshan. But why do we have to reduce? Can someone else answer? Is it really mandatory for us to reduce an expression?
To decrease the number of gates.
Okay,
Logic.
and then, and then, so what's the advantage of having less number of gates?
The circuit will be small.
Yes, the circuit becomes smaller, and not only that, if you think with economical point of view, it's going to be very economical having less number of gates and doing the same function, isn't it? It's like having just 5 people doing the work of 10 people, isn't it? So economically also it's going to be feasible. Fine. So this is one of the advantages of reducing a larger circuit, okay, into a smaller circuit, but having the same functionality. Okay, fine. So that is one part of it. And the other thing is that, we should try and enhance and as much as possible try to get our circuit minimized. The reason why I'm telling you this is every transistor, okay, that you see, or every single wire that you see, every 10 mm, okay, for example, a millimeter increase in wire length can actually increase the resistance and capacitance in the circuit. Okay, so you can imagine if in case I reduce the gates, okay, and then in gates, that there that is built of transistors, and because of which what is going to happen, I am totally going to reduce the delay, and my circuit is going to be faster, responsive. As soon as I give my inputs, they are going to appear at the outputs, right? Okay, so simplification, can you tell me some techniques that you have studied in your subject for simplifying Boolean expressions?
By using laws of Boolean algebra.
Okay, what kind of laws are we using?
Identity law.
Hmm, okay, fine. Sai Kumar. Sai Kumar,
Yes, sir.
yes. Can you continue with your friend's answer? He has told some laws. Are those the only things that we can use for reduction of a Boolean expression, or there is something else also? This is just a revisit of what you guys have studied in your theory. Anybody else wants to help him?
So to get less number of
Hmm.
logic gates, if we simplify the Boolean expression, then we get a simplified version which
Okay.
has less number of terms. So we have to use less logic gates than the original Boolean expression might
Yes.
contain.
Yes, that's fine. Now my question, that was my first question. My second question now was, what are the other things that we use, other techniques that we use for the simplification?
Associative law,
Exactly.
distributive law,
So
Okay.
associative law, distributive law,
Hmm.
uh,
commutative
Absorption,
law.
commutative law, and then one more.
absorption law,
Idempotence laws.
Morgan's law, sir.
idempotent, De Morgan's,
De
right?
Morgan's
De
law.
Morgan's.
Exactly. Good, good. So these are some of the laws that we used. Apart from this, we use different techniques. Can you name a few techniques? Now you have specified only about the algebraic point of view. So in algebraic point of view, these all laws comes into picture. But we have used a whole different method, right? 2, 3 methods we have discussed in your first module. How about MEV, map entered variable? Don't you think that is a method of simplifying an expression?
Yes, sir.
Yes. Then how
Yes, sir.
about your implementation table? Have you come across implementation table?
No, sir. No, sir. We
Okay,
don't
you
know
will
about
be
that.
learning that. Okay, so that's also one of the techniques used for reducing the Boolean expression. Now that we have known the techniques how to simplify a Boolean expression, in the question here they have given K-map, okay, and realization of simplified expression using basic gates. Now basic gates realization is very easy, isn't it? Do you all have any doubts in basic realization, basic gate realization? For example, y is equal to ab plus cd. Is it difficult for you to implement it using basic gates?
No, sir.
No,
No,
sir.
right? You will just need an AND gate, and then you will need an OR gate. 2 AND gates, 1 OR gate, AB plus CD. Example, right? Now, this one to be converted to our standard form. What is the standard form? Into your NAND form or NOR form, right? So, are you all aware of this conversion? Converting it into standard form?
Sir. De
Yes.
Morgan's.
Yes, you can use that law. And also
De
what I will be
Morgan's.
doing is I will be showing you one of the method, okay, the other method that you can employ for conversion of any logic gate into its standard form. Okay, fine. Now, are you all able to see this? My handwritten notes?
Yes, sir.
Yeah, okay. So we will just quickly see one example, okay, for NAND and NOT implementation. So basically there is a rule, okay, that if in case a question is asked, implement this equation using your NAND gates, okay, then as usual you will be implementing using your logic diagram, okay, which means using your basic gates. And then in that basic gate, you have to insert a NOT gate at the output of AND. And at the input of OR gate, you also have to include a NOT gate. So this point number 2 is very important. I hope all of you are maintaining an observation notebook separately for this lab purpose. Yes, are you all? I want you all to maintain a separate notebook, okay, for this lab. So that's going to be your observation book. Are you all clear with this, students?
Yes, sir.
Okay, because at the end of the lab, okay, I would like to have your scans uploaded onto Google Classroom. I have already posted the assignment. Okay, so the assignment for your lab today is that you have to note down whatever is taught and whatever things that will be posted. You have to make note of that and you have to write it on your notebook and you have to scan it and upload it on the Google Classroom, right? Okay, so now let's get back to this NAND implementation. So you will be basically at the first stage implementing a normal circuit using basic gates, and then you will be inserting a NOT gate at every AND output and input of every OR gate. So if there are double NOT gates, as you all know, what happens? It nullifies, right? Because the input and the output of a double NOT gate is going to be the same. So I can nullify it. And then at the last step, replace all gates by NAND gate. For the NOR gate, what is going to happen? Only point number 2 changes. Okay. So inserting a NOT gate at the output of OR gate. Okay. Always remember whenever there is a NOR implementation, NOR. So your NOT will come after OR gate. So NOT gate at the output of OR gate. And the reverse happens to AND gate. Okay, and input of AND gate. So only this point number 2 is reversed for NAND and NOR implementation. So let's quickly see one example. Okay, and you will understand as to how it is done. Realize an XOR gate using NAND gate, and I have an expression. So you all know the expression of your XOR gate, right? AB XNOR, AB plus A bar B bar, right? So I will be doing my normal implementation, okay, where A, B gets multiplied, okay, then A bar, B bar, I need the help of an inverter. So A bar, B bar comes here, and then to this, I need to add. So as per our rule, we had to insert a NOT gate after AND gate, right? So we have AND gate here. I have a NOT gate. So AND gate is here, NOT gate, and NOT gate in front of OR gate. So which means at the input of OR gate. So finally what happens? We can convert everything to NAND gates. So this single inverter, okay, this single NOT gate can be actually represented like this. So both the inputs are shorted and I just have single input given to it. So all the gates can be replaced with NOT gate. Now here I have a double NOT gate. So what is going to happen? It's going to get nullified, and this AND is going to get converted to NAND. AND is getting converted to NAND, and this OR will get converted to NAND with the help of these NOT gates. So guys, is this simple for you? Yeah, have you understood how to implement this NAND gates? Students, I'm waiting for your response. Is it clear whatever I have explained so far?
Yes, sir.
Okay, fine.
Yes, sir.
Thank you. Thank you. So the same thing happens to your NOR gate. Okay, so for NOR gate, what we do is we insert a NOT gate at the output of OR gate. Okay, and at the input of AND gate. So any equation, implement with basic gates, put them, okay, and then you can actually convert, okay, all the gates into NOR gate. If there are double inverters, you nullify it. If there is a single inverter, convert it to whichever expression. For example, here it's asked NOR uh, using your NOR gate. So this will be your NOR gate implementation, right? So let's get started with your experiment now. Okay, I hope you are very clear with K-map and very clear with basic gates. And now that I have taught you how to implement using universal gates, so let's get started with experiment number 1. Okay, so here you will be needing your digital IC trainer kit. Okay, I will be posting a video wherein you can actually look into the practical concepts or we have done practically, and that video can actually be seen. Okay, a digital trainer kit. Patch cords are nothing but your wires. Then we need 7400 IC. Okay, then 7402 IC, then 7432, 7486. What are all these numbers, by the way? What are all these numbers? 7400, 402, 432, 486. What are all these?
Series number.
A series of what? of students. I want you to feel free. Okay, please. I want you to ask me questions. I want you to interact. Be interactive. Okay. So all of you have a look at this. You're able to see my screen?
Yes, sir.
Yeah. Okay. So for your NOT gate, it is 7404. Okay. And your NOR gate, the IC number is 7402. Similarly, for your AND gate, okay, NAND gate, OR gate, XOR gate. So these are the important gates we will be using for this experiment. And this is nothing but pin number 1 is your input. At pin number 2, I get my output. So you cannot connect input at pin 2 and expect the output at pin 1. No, not happening. Okay, so this is a 14 pin IC where your 7th pin gets connected to ground and your 14th pin gets connected to a higher potential VCC or VDD. Similarly, every gate's configuration is here, okay, where your 2, 3 is input and 1 is the output for your NOR gate. Okay, so you can see that across. Okay, so I will be sharing this also in your classroom. So I want you to make a note of this, okay, and put it up in your observation notebook. Right. So now let us concentrate on the experiment that we have today. So your implementation, okay, the first experiment that you have is with regards to your basic gates. Okay, this is just for your practice that I have put up here, okay, to verify the truth table of gates. Okay, and you all know what is the truth table of NOT gate, right? 0 1 1 0 input a, y is equal to a bar, then realizing using NAND, both I short, then I get it. Then using NOR also I short and then I get it. AND gate truth table, this is the representation of AND gate. Okay, then how do you realize AND gate? Okay, using your universal gates. Okay, that's also there. So what am I doing here? I'm connecting an inverter. Okay, this is NAND actually, NAND, and then I connect an inverter which is NOT. So NAND plus NOT will actually remove the N from here, and what happens? It actually gives me only AND gate. Okay, next. Similarly, the same thing with your NOR. Okay, you have your truth table and your NOR implementation. Okay, your OR gate, your XOR gate. You know that if the values are same, the output is 0. If the values are different, okay, then the output is going to be high. So that's the specialty of your XOR gate. And one more thing that you can recall is XOR gates are used like comparators. Okay, it can actually compare between values. If it is different, then values are 1. If it is same, then values are 0. Like sort of comparator XOR, right? Then XOR implementation using NAND, which I have shown in my notes, right? Then XOR using NOR, this one also I have shown in my notes. Okay, right. So for your experiment, okay, for the first experiment, okay, you will be actually looking into simplifying this expression. Okay, you have two expressions here. Can someone tell me, is this a min term or a max term? The second equation and the first equation.
Min terms.
Yes, it's a
Terms.
min term. So which means it's a sum of product or product of sum.
Sum of
Sum of
products.
product.
Yes, good. So if you look at the first equation here, okay, it's not in the standard form. When I say it's not in the standard form, it has only AB here, it has only BC here, there's no A, here there's no C, it's not in standard canonical form, right? So we have to convert it into standard form and then start off with our reductions. Okay, so we will be using here the Boolean algebra. So C plus C bar. What is C plus C bar?
One, sir.
One.
Good. Anything that gets multiplied with 1 will be the same value. So AB, it's multiplying with 1, which means it's not harming the value of AB, right? AB remains the same. So similarly here, B bar C, it's getting multiplied with A plus A bar, the same explanation that I gave. Then you'll be multiplying it, okay? And then now you'll be taking common A bar C, and then you'll be getting this equation. Then similarly AC plus this part becomes 1, right? Then again here AC plus A B C bar. Now here if you can see I have C as common, then A and A bar goes off, and plus ABC, so it becomes C plus uh, A B C bar. Okay, now using my absorption law, okay, my distributive law, this becomes C plus AB, right? Okay. Now the other method that we'll be using here is your K-map. Okay, so what you can do is you can actually put those values here. Okay, so whatever is specified, okay, whatever is specified, you can actually put those values here into K-map, and you can reduce it. Okay, you can get a quad here, and you can get dual here, 2 ones and then 4 ones, and accordingly you get a minimized function. If you have to represent the truth table, right, y is equal to a plus bc. Okay, so here what you can do is you have to multiply ab, okay, and that value should be added with c. So here you see 0 into 1 is 0 plus 0 is 0. So 0 into 0 is 0 plus 1 is 1. Okay, so this is how your truth table gets generated. So once you have the truth table, now it's easy for you to implement, right? We have the equation here, y is equal to ab plus c, which is very simple, right? So I will be using an AND gate 7408, then I'll be using an OR gate 7432, and the outputs are taken and given here. So my final output will be at terminal 3 of OR gate, which is ab plus c. So these are all your pin numbers, okay? The diagram which I showed you, right? So we will be using that for the connection. Now, with only NAND gates, yes, we can convert it, right? You can put a uh, NOT gate here, right? NOT gate. So this 2 gets converted to NAND, and then I have a single input here, so I have to use a inverter here. Okay. Then with NOR gates also, as I have taught you, you can implement it. You can convert it to your standard NOR form. Equation 2 can be implemented using K-map, right? So it's as straightforward as possible, right? So which means how many squares do I need to have in my K-map? Students,
8, sir.
8. How did we come with 8?
That is 3 bit, like 2 power 3.
Exactly. So 2 power 3. So we have
8.
to have 8 squares. Good. Thank you, Bhumika. So once we have the K-map, okay, you can only put ones where whatever the values are given here, okay, at 0 square, 1, 4, 5, 7, right? So at those squares, you can actually make high, and you can do the grouping, okay, you can do the grouping. And once you have the equation, you can actually come up with your truth table. Then once you get the equation, actually, it's very simple to get the uh, basic gates, and then the universal gates. So for this, what you need to do, you need to actually connect, you will get ICs, okay, specific IC 7402. Okay, so this IC will have to be connected as per your circuit diagram. So what is the circuit diagram? Pin number 2 and 3 will be connected to each other and given to A input. Okay, 5 and 6 will be connected and given to B input. 8 and 9 will be connected and given to C input. Now, what is this ABC? It is nothing but your 0, 0, 0. Okay, you have 3-bit combination here, right? 000 to 111, right? So all these combinations are nothing but your inputs. So as you give your inputs here, okay, accordingly your gates are connected, and then you get your output, final output, with whatever equation that you have realized with the K-map. Okay, and every IC will need some supply to work. Okay, so which means we will need about plus 5 volts for the supply. Okay, and we connect it, and the next part what we do is we verify the truth table. So during your exams what we do is we tell you to show, okay, show me 110, so you should be getting 0, which means your LED should not glow, your light should not glow. Similarly, I will tell you, okay, show me 001 for this combination, so your output should be 1. Okay, so like that you will be verified with your lab experiments. Then you'll be verifying the truth table. Then you can switch off the power supply and disconnect the circuit. So this is the procedure, simple procedure for your lab. Okay. So now what we will do is I will be posting the video links, okay, that you need to watch. And if there is any doubts, right, we will have another meeting, okay, and we will try to clarify those doubts. Okay, so till here, students, do you have any doubts, any concerns with whatever was discussed so far?
No, sir.
Everything is fine, right? So we have a
Yes, sir.
basic gate, we have an equation, and then we are converting it. If it's asked to minimize, you minimize it using your K-map or using your MEME method, okay, whatever method, but just follow whatever is asked in the question. So that can be followed and convert them into its standard form, which means your universal gate form, NAND and NOR implementation. So um, what I want you to do is I want you to look into the video. Okay. Also, I will be posting this session that we have had so far, so that you can actually pause the video and you can note down. Okay. You can note down all that I have taught you and put it on your observation notebook. And by the end of the day, okay, what you can do is you can scan it. Okay. You can scan it and you can upload it in the Google Classroom. Okay. So students, can we end the meeting now?
Yes, sir.
Okay, fine then. Thank you.
Thank you, sir.
Welcome.